Hi everyone. So this stage or this step of the project is going to be looking at building the logic that takes the output of the counter here, or the state of this counter, and turns it into something that will eventually be human readable on our 7-segment display. And so at the moment what we have is our astable providing pulses to our counter circuit. And the counter circuit, it just has one output high at any one time, and it will cycle through them. And we've connected after this, or on the 7th pulse, we've connected that to the reset, which takes it right back to the first one. So it's going to count one of these high will be high, then the second one will be high, and it'll do this 6 times, and then it will reset back to the first one. So now this logic, we're going to be using something called diode OR gate OR logic. And the way that we can connect that is, well, the first thing I'm going to need to do is disconnect the power from the thing so we don't damage anything accidentally. And I'm going to be using 3 diodes that are connected onto a single resistor, each one. Now I've cut mine and bent them so that they are short and prepared. You don't need to necessarily do that. So we can get that in there. Oops. Let's try. Okay. So one diode. And because I need to connect 3 diodes with their anodes. Now the anodes of these diodes, which is the negative end of it, is marked with a black line here. So the negative side of this black line of each of the 3 diodes, they all need to be connected together. So that means that all 3 of the negative ends need to be connected into the same row here. Okay. So I've got one of these diodes in with the black end in this bottom side. So the next diode I'm going to put in, the positive side, which is the side on the red end, I can't put in the same row as this one because I want it to be connected separately. So I'm just going to use the row right next to it. But the negative end, the anode, the cathode of our diode needs to be connected to the cathode of this diode. And so it needs to be in one of these holes here. So I'm going to be putting it in. You'll see in a moment. So this one, it's connecting into that hole there, and this hole there. Okay, so now the 2 anodes, the 2 positive sides of my diodes, are in different rows, they're not connected. And the 2 cathodes, which are the negative ends of my diodes, are connected together. And I'm going to do exactly the same for the 3rd diode. It's going to look like that. Okay. So now all 3 of those diodes, their cathodes are connected together, their anodes are not connected together, and we need to connect the anode to 0 volts using a resistor. Now the value of the resistor isn't super important. I found experimentally that if the resistor value is too low, it doesn't work properly, and if the resistor value is too high, it doesn't work properly. 100k ohms seem to work well. But I think 10k would also work. Anything between 10k and maybe 470k would be fine. Okay, now to connect these onto the output of our counter circuit, look at the diagram. Where the D1, D2 and D3 are going to be these diodes here. And you can see that they are connected to Q0, Q2 and Q4. So Q0, which is pin 3. So don't forget that the names on the pins and the pin number aren't necessarily the same thing. So Q0 is the name of the output pin, but it is actually this pin 3 here. So I'm going to have to connect pin 3, this one, onto one of these diodes. So using a piece of breadboard wire, I've already cut to length. I can do that. Just got to get the right one. So pin 3, there it is there, and one of these diodes. It doesn't actually matter which diode you choose, as long as you keep track of it. So pin 3 is connected to one of the diodes. Pin 4 is also connected to one of the other diodes. So again, piece of breadboard wire, already cut to length. Okay. So pin 3 connects to this diode. Pin 4 connects to this diode, and finally Q4, which is pin 10, connects to a diode. So I'm just going to use another piece of breadboard wire here. Pin 10 is, so we've got 8, 9, 10. So this one here is pin 10. And it connects across like so. Okay. So that's the first set of logic. I'm going to go ahead and build the next set of logic, but I might fast forward it so that rather than annotating every single step, because it's the same sort of process. We look at the pin number on the diagram, and we just connect them to the corresponding diodes. Now, in some cases, we have pin numbers connected to more than one diode. So if you have a look at this diagram, you can see that pin 4 is connected to this diode here, but it's also going to be connected to another diode in the next set. So all we can do there, we don't have to go right back to the chip. We can actually daisy chain off this connection here. So you'll see that a couple of times. Okay, so we've got, for this one, we've got pin 1 connected, pin 2 connected, and pin 4, which I connected via this short link here onto the previous logic gate. Putting exactly the same thing again, but just for the final gate. So I've now connected all 3 of the logic diodes up, and the way we can test this, we should see no change in that behaviour. We should see no change in the output of our counter circuit, so we can just check that again. So just making sure, so I'm going to put on pin 10 again, and you can see it pulses high periodically. And now the output that we of this is the connection across the resistor here. So if I look across this resistor, so it doesn't matter which one, let's do that one, you see it should go high periodically, there we go. This one should do the same, should see a voltage every so often, yep. And again, on this third one, you should see that. Okay. Now normally, at this sort of stage is where I would connect this to an oscilloscope to see it actually working its magic properly. So I'll see if I can bring up what it would look like on a simulated circuit.
Okay, so to show the behavior of the astable on what would look like an oscilloscope, I can use the Circuit Wizard simulator to do the same sort of thing. Now in Circuit Wizard we have a probe that we can add, which will show what it looks like. So when I press this button here, it'll run the simulator, and down the bottom here we can see, well, looks like it's pulsing too quickly for it, so let's just slow it all down a bit. There we go. So you can see the pulses happening about 10 times per second, and which is actually what we saw. So we had the 100 microfarad there in place, and we could actually watch the pulses happening. But when we took the 100 microfarad away and made it just the 10 microfarad, it was too quick to see, and that's what we were seeing down here before. It was just transitioning, doing exactly this, just so quickly that it's like a blurred line. So this is what the output of the oscilloscope would look like, and if I move this onto one of the outputs of our counter, what you can see here is that it's, instead of pulsing every time, it's pulsing once every 6th pulse. And the pulses also look a little bit wider, and that's because the way the counter works is that the output will be high for the entire duration of a full pulse. So even though the clock here has gone low, this will stay high until it changes it to the next output. Okay, and so the output of the logic gates is going to look something very similar to that. Okay, so this one, we can see it's every odd one, and this one is going to be a little bit different, and this one's going to be a little bit different as well. And this is the way that this is encoding the numbers. So this will be high for every odd number, and this will be high for every number where we have to add 2 into it to make the number, and this will be the number be high for where we have to add 4 into the number. This is just how binary works.
And that's the end of step 3.